In recent years, the development of artificial intelligence has revolutionized the world of technology. Among the most powerful tools in this field are neural networks, which are a type of algorithm that can analyze complex data and recognize patterns that are difficult for humans to detect. Neural networks are already being used in various applications, from self-driving cars to facial recognition software. In this video, we'll dive into the world of neural networks and explore how they work, what they are used for, and their impact on the world as we know it. Whether you're a tech enthusiast or simply curious about the inner workings of AI, this video will provide a comprehensive overview of neural networks and their potential. Let's get started. Section 1. What are neural networks? Neural networks are a type of machine learning algorithm inspired by the structure and function of the human brain. They are designed to recognize patterns in data and make predictions based on that data. A neural network consists of layers of interconnected nodes, or neurons, that process information and pass it on to the next layer. Each neuron in a neural network is connected to several other neurons, and the strength of those connections can be adjusted during training to improve the network's accuracy. Neural networks have been used to solve a wide range of problems, from image recognition and speech recognition to natural language processing and game playing. They are a powerful tool for solving complex problems and making predictions based on large datasets. Section 2. Neural Network Architecture. Neural network architecture refers to the organization of neurons and their connections in a neural network. It is the design of the network, including the number of layers, the type of layers, the number of neurons in each layer, the connections between the neurons, and the way the data flows through the network. There are many different types of neural network architecture, each with their own strengths and weaknesses. For example, a feed-forward neural network has a simple architecture, with neurons arranged in layers that only allow data to flow in one direction. Convolutional neural networks, on the other hand, are specifically designed to analyze image data, with layers that can identify edges, shapes, and patterns. The architecture of a neural network is critical to its performance, and researchers continue to develop and refine new architectures to improve the accuracy and efficiency of neural networks in various applications. Section 3. The learning process. The learning process is the most important part of a neural network, as it is the method through which the network becomes capable of making predictions or recognizing patterns. There are three types of learning processes: supervised learning, unsupervised learning, and reinforcement learning. Supervised learning is the most common learning process for neural networks. In supervised learning, the neural network is given a set of inputs and the corresponding outputs that the network should produce for those inputs. The network then adjusts its weights and biases to minimize the error between the actual outputs and the desired outputs. Unsupervised learning is used when the network is given input data without any corresponding output data. In unsupervised learning, the network must find patterns or relationships in the input data on its own. This is often used for tasks such as clustering or dimensionality reduction. Reinforcement learning is a learning process in which the network learns by receiving feedback from its environment. The network receives a reward or punishment based on its actions, and it adjusts its weights and biases to maximize the rewards and minimize the punishments. The learning process of a neural network is iterative, meaning that it continues to adjust its weights and biases until the error rate is minimized or the desired accuracy is achieved. As the network learns from the data, it becomes more accurate and better at making predictions. Section 4. Applications of neural networks. Neural networks have a wide range of applications in various fields, including computer vision, natural language processing, speech recognition, machine translation, robotics, finance, and healthcare. In computer vision, neural networks can be used for tasks such as image classification, object detection, and segmentation. Natural language processing relies on neural networks for tasks such as language modeling, sentiment analysis, and named entity recognition. Speech recognition and synthesis systems also use neural networks to improve accuracy and naturalness. In robotics, neural networks can be used for tasks such as object recognition and grasping, motion planning, and control. In finance, neural networks can be used for tasks such as stock price prediction, fraud detection, and credit risk assessment. In healthcare, neural networks can be used for tasks such as disease diagnosis and drug discovery. The applications of neural networks are constantly expanding as new research is conducted and new use cases are discovered. The potential of neural networks to improve and automate a wide range of tasks makes them an important area of study and development in the field of artificial intelligence. Section 5: Limitations and Challenges. Although neural networks are very powerful, they are not without limitations and challenges. Here are some of the main limitations and challenges of neural networks. Data requirements. Neural networks require large amounts of data to be trained effectively. Without enough data, the network may not be able to learn the underlying patterns and relationships in the data, resulting in poor performance. Overfitting. Overfitting occurs when a neural network is trained too well on a particular set of data and becomes too specialized to that data. This means that the network may not perform well on new data that it has not been trained on. Interpretability. Neural networks are often referred to as black boxes because it can be difficult to understand how they arrived at a particular output. This lack of interpretability can be problematic in situations where it is important to know how the network arrived at a particular decision. Computationally expensive. Neural networks can be computationally expensive to train and run, especially for large datasets. This means that they may not be practical for use in certain applications. Lack of generalization. Although neural networks are capable of learning patterns and relationships in data, they may not always be able to generalize to new situations. This is because they are trained on specific data and may not be able to adapt to new situations or data. Data bias. Neural networks can be susceptible to data bias, which occurs when the training data does not accurately represent the real-world situations that the network will be used for. This can result in the network making incorrect or biased predictions. Security concerns. Neural networks can be vulnerable to attacks and may be susceptible to adversarial examples, where small changes to the input data can cause the network to make incorrect predictions. Despite these limitations and challenges, neural networks have become an important tool in many fields, from computer vision and natural language processing to finance and healthcare. As research in this area continues, it is likely that many of these challenges will be addressed, making neural networks even more powerful and versatile. In conclusion, neural networks have revolutionized the field of artificial intelligence and have shown their potential in solving complex problems. These systems have already been applied in various fields, including image and speech recognition, natural language processing, robotics, and medicine. However, like any technology, neural networks have limitations and challenges that need to be addressed to unlock their full potential. The field of neural networks is evolving rapidly, and researchers are constantly exploring new architectures and learning algorithms to enhance their performance. As more data becomes available, neural networks will become even more powerful in analyzing and interpreting complex information. We can expect to see more practical applications of neural networks in the near future, including self-driving cars, personalized medicine, and intelligent virtual assistants. At the same time, we must be aware of the limitations of neural networks and continue to work towards improving them. Neural networks can be prone to errors, particularly in situations where the data is incomplete, noisy, or biased. Additionally, neural networks can be vulnerable to adversarial attacks, where malicious actors can manipulate the input data to deceive the system. Overall, neural networks have the potential to transform many industries and change the way we live and work. As this technology continues to advance, we can expect to see more exciting developments and innovations in the years to come. Thanks for watching.